Let's move on now to discuss the probability density function of the state of a GBM process and how it can be used to calculate expectations and probabilities. If you recall, the PDF of a geometric Brownian motion process is a log normal distribution. We might want to plot that PDF for a specific GBM process. Here, for example, with parameters mu equals 0, sigma equal 0.5, and a starting value x of 0, 100. And we'll look at how that PDF evolves over time from t equals 0 to t equals 5. As we do that, we see that the mean of the process shifts downwards and the standard deviation increases with the square root of time. Why does the mean of the PDF move down? It's because the drift in the mean of the process is t times mu minus sigma squared over 2. Here, mu is 0, so the drift is t times minus sigma squared over 2, a negative value. So the mean is becoming smaller. If we change the GBM process to have a positive drift, say mu equal 0.5, and let's extend the plot range a little so we can see what's going on. Here we see the opposite effect. Now the drift, t times mu minus sigma squared over 2, is positive. And so the mean is shifting over time to the right, it's becoming larger, as before the standard deviation increases with the square root of time. Well, knowing the PDF means that we can calculate the probabilities of various expressions. So if x is a GBM process with parameters mu, sigma, and x0 as before, then the expectation of, for example, x squared at time t is given by this expression. Why would we want to calculate the expectation of a function such as x squared? Well, arguably we wouldn't. But as we'll see when we come on to discuss derivatives, there are functions of a GBM process whose expectation we are very definitely interested in. Knowing the PDF of the state of a GBM process enables us to calculate the probability of certain events. So, for example, let's say we have a GBM process with parameters mu, sigma, and x0, and we want to find the probability that the state at time t, xt, exceeds the starting value, x0. And we can directly compute that probability. It's 1/2 of the complementary error function of minus t times mu minus sigma squared over 2, all divided by the square root of 2t sigma squared. Let's take a look at that expression for a range of different GBM processes with sigma set to 0.5 and starting value, it doesn't really matter, but let's say we set it to 100. And we'll look at the probability over time for processes with drift mu set to 0, 0.125, and 0.25. Now, as you can see, the blue line refers to the GBM process with drift parameter mu of 0. And in that case, as we saw before, the mean in the process has a negative drift of minus t times sigma squared over 2. Consequently, the probability of exceeding the starting value declines over time from t equals 0 through t equals 6. Now let's look at the case where mu is set to 0.125. Well, if you remember, the calculation is t times mu minus sigma squared over 2. In this case, sigma squared over 2 is 0.125. So the product of t times mu minus sigma squared over 2 is exactly 0. And therefore, there is a 50% probability that at time t, the state will exceed the starting value of 100. And that probability remains constant over time. And then finally, if we set mu to something like 0.25, then the drift in the mean process is positive, and the probability of exceeding the starting value increases over time.